So I sent you the link for the live notes also, so you can take notes as usual. Well, usually it's me, but
Is that working for other people?
yeah, everybody.
It doesn't come up.
Yeah, some people. Well, there are usually 10 to 15% connected, so.
Okay.
Worked for me.
Yes.
The notes have been very good. I've been reading some, and it's been
trying my best.
quite nice summaries.
Just when I'm talking, I can't do it.
Right.
How do you read the notes? If I have to use the same link and get off VPN. Is that the idea?
I think so. Yeah. Mm-hmm.
Okay.
We will share it on the on the meeting page later.
Okay.
So in the original program, there were a few words on SolarSoft, and we had proposed to Jack Ireland to say a few words. I don't know if you want to say a few words now, Jack.
Yes, I can. Apologies that I can't. I don't have a presentation, but that's okay because there's not much news for SolarSoft. SolarSoft is still being funded by the SDAC, and the lead is Lockheed Martin. We fund them to maintain SolarSoft. If you go to the SolarSoft webpage, there's a list of latest significant changes. So SolarSoft is continuing. As you know, it's an IDL-based, primarily IDL-based software package. I guess the most recent significant change was since NASA dropped the use of anonymous FTP connections, then we had to change the SolarSoft update method. As you may know, SolarSoft has developed its own way of updating itself years and years ago, and that's worked up until the fact that check-ins to the repository at NASA, where you get the updates, worked via FTP, and then for security reasons, NASA dropped FTP, so that had to be reworked. And so that was a combination of folks at NASA and Lockheed Martin who got that fixed. So that seems to have worked okay. We got surprisingly few queries about the update method, about the change. So it seems to have worked. And yeah, that's about it. So SolarSoft continues, and will probably continue as long as instrument teams use IDL and SolarSoft as a basis for their more specific software. So that's about all I have to say about SolarSoft.
Okay, thanks. Any question?
I'm wondering, an idea that I've had for a long time is to make the prep routines in particular be kind of a web service so that you don't have to actually invoke, and you can just get the prepped file without having to have your own instance of SolarSoft. Is that something that anybody's thought about anymore? Or?
There was like an experimental version of that 10 or 15 years ago, but I don't think that is going forward anymore. I'm not, nobody, as far as I'm aware, has that kind of web service. It would be a very nice thing to have, because then we would basically, nobody would have to, as you say, have a local version of SolarSoft.
Right, so you could run SunPy and just have some nice little interface that goes off and runs a prep on whatever you want.
Yes. So those legacy systems, assuming that instruments going forward will be using Python, then it would be a nice addition to the data analysis environment if we could.
Seems to me it's the main thing that SunPy is reproducing all those prep routines, which is where a lot of the code goes.
Yeah, probably
so
not all instruments, but yeah.
Yeah, IHDEA is a successful example of a Python implementation of some of the AIA processing routines. AIA prep routines, but I'm not sure there's that many other. I mean, the level of effort, for example, to reproduce LASCO processing in Python would be considerable. So
that's right. So why reproduce it? Why not just have this little web service and run it in the background? Anyway,
it's a good idea, but nobody's proposed to do it. So
I keep suggesting it to various people, but I don't get enough traction. Maybe I just self-fund it.
that can attract some attention.
Yeah.
Okay, thank you. Any other short question before we go to the next one? Okay, so next one was about SPEEDAS. And Jim Lewis has a presentation, so you have 10 minutes.
Okay, I hope people can hear me.
Yeah. Can you share your screen?
Yes, let's see, maybe. Okay, hopefully that'll be the display view. Can you see the first slide? Okay, excellent. So, okay, well, I'm Jim Lewis. I'm the software manager for the SPEEDAS development project. You can see our contact information here. And today I want to talk a little bit about some of our SPEEDAS interoperability tools and metadata considerations and where we might want to go in our future development. So what I'm going to do is I'm going to present a simple workflow and then think about how we might accomplish that using some of our generic tools like C2Web data access or HAPI or DOS2. And then I'll go into a little bit of the metadata issues that come into play and then how that might affect our future development and maybe the development of some of these access methods. So the workflow I'd like to consider is this. You could consider loading Themis satellite positions and Fluxgate magnetometer for a time range of interest. And then we want to pass that to a field model. So for the modeling, we would need to load some solar wind parameters from OmniWeb. We might want to load some geomagnetic indices from the Kyoto World Data Center. And then we pass all that stuff to the GeoPack library and say the Sigonenko 07 model. And then we can generate expected field values at the Themis times and positions or do field line tracings to the equator or to the ionosphere. And then we might want to plot and compare the Themis observed fields to the modeled fields. Now that's pretty straightforward in SPEEDAS, just a few lines of IDL code or just a few clicks in the GUI. And that's because SPEEDAS already includes some full-featured load routines in the various plugins. And these routines, they've been written, they've been vetted. If there's any adjustments needed or additions to the metadata, that's done in the load routines. But what if we want to use a data source that is not currently available as a SPEEDAS plugin? And the example I thought of was a few months ago, we had a Bepi Colombo flyby, and we had a researcher who wanted to do some comparisons between their instruments and Themis observations. So can we do that with the current generic data access tools? So This is not a tutorial, so I'm going to fly through this really fast just to give a sense of what's available in SpeedAS. This is our data loading menu. And you can see we have you can load data from the plugins. You can load from Happy. You can load via CEDA and DOS2 is available, but that's command line only at this point. This is our GUI load panel for the plugins, and you can see all these tabs are different missions we support. This tab I have displayed is the geomagnetic indices. This is our panel for doing field modeling, and the way this works is you select a position variable that's already loaded into SpeedAS, and then you can specify some of the other solar wind parameters, magnetospheric parameters. Just choose a set of variables, and then you have the options to model at the position or do the field line tracing. This is our data analysis panel, and on the left we have the data items that are already loaded in SpeedAS. You can move them into the middle pane, the active data, and then down the right-hand side, you have various analysis steps that you can apply. In particular, we have an option for doing coordinate transformations. The important thing there is you sort of have to know where you are before you can know how to get to the coordinate system you want to be in, and that'll be important later. This is our CEDA interactive data chooser, and so in this panel, when you're connected to CEDA, you choose a mission group, and then you drill down to the instrument types. You click on Find Data Sets, and then it populates that middle pane with what's available from CEDA. You pick a time range of interest, and then click on Get CEDA Data, and it all gets loaded into SpeedAS. This is some of our Happy code. This happens to be one of our crib sheets showing the command line usage of Happy load data. And in this particular example, this loads a few data sets from Voyager and Cassini. And you can see it's just a couple of lines, very simple interface for each data set. And here's what you get when you load it and plot it in SpeedAS. This is Cassini magnetometer data. So very nice, a nice plot. It's you can do many of the same things you could do with data sets that are supported by SpeedAS plugins. This is our interactive GUI Happy Load interface, and that works quite similar to the CEDA panel. Choose a Happy server. You can get the server info. You can list the data sets. You can pick a particular data set and get information about it. And then again, you pick a time range, and you can load the data via Happy. And this is showing some data, some Themis data that I've loaded via both Happy and CEDA. The top panel is via Happy. And that is via CEDA Happy server, by the way. The lower panel is what we get directly from CEDA through the file interface, the web service. So they're a pretty good match. I'm not sure what happened to the Happy data. You can see there's a little data gap where I've got the cursor bar. I'm not sure what happened there. I would expect those to be the same data set, but anyway, that's a matter for another time. I do want to point out that in the CEDA case, we did get a lot more metadata, and so you can see we have a units notation on the lower left, and on the lower right, we have labels for all the traces. Here's our command line DOS2 interface. This is a crib sheet showing how to get some data from Juno, and again, you choose the server URL and add start time, end times, and then query for data sets, and then you could sort of dig down to the data you want and the metadata you want. And this is the result. So So it's nice to see that we can load spectrogram data and have it be plotted. As you can see, we have nice labels. We have the y-axis labeling on the left. We have the frequencies in hertz. And on the right-hand border, you see we have the Z values corresponding to the color map. So let's talk about the differences in metadata handling. CEDAWeb serves ISTP-compliant CDFs, but that's not always the whole story. There are some very useful non-ISTP attributes that are going to be necessary if you want to do things like coordinate transformations. So for example, a coordinate system, that's optional. It's not an ISTP required attribute. And so some data sets have it, some don't specify it as a variable attribute, although it might be present like in the name of the data set or in the axis labels or something similar. But in those cases, we can't really expect SpeedS to figure it out on its own. So the user might have to manually add that information before passing it to a model or doing a coordinate transformation. So the happy results we get, it's good for getting access to the raw data, and at least in our implementation in SpeedS, I think we could get the units and things like bin boundaries, bin centers, but as far as I know, there's not a generic way to get other parameter attributes. And I hope someone will correct me if I'm wrong on that. It might just be incomplete implementation on our part. The DOS2 service, I took a look at the interface control document for that, and it does seem to support attaching arbitrary attributes to data quantities. DOS2 is still fairly new to the SpeedS developers, so we don't have a lot of experience using it with different data sets, so we don't really have a sense of what the common practices are and what we can expect to be available. So, so to answer the question I raised at the beginning, where we want to load data through one of these services and then possibly pass it to a field model and perhaps do some unit conversions or coordinate transforms. So in CEDAWeb, there's a good chance you would be able to do it. It depends on whether the correct attributes are present in that data set. For Happy and DOS2 at this point, you would probably have to do some manual work and you might have to have some additional knowledge to be able to set the coordinate system at least correctly and be able to interoperate with the rest of SpeedS. So then, even if we do get our hands on the metadata, will SpeedS necessarily know what to do with it? So I just want to raise an issue. Let's say we're talking specifically about Earth-centered inertial coordinates. Now in SpeedS and in FEMIS, we call that GEI coordinates. Another mission, you also see ECI in the literature. MMS uses J2000. Now, are those systems all synonyms? Unfortunately, they're not. What SpeedS refers to as GEI, that's actually true of date, equator, and equinox. J2000 is mean as of the J2000 epoch. And if you see someone using ECI, don't really know what you might be getting if that level of precision matters to you.
Yeah, I was going to ask you about that. How do you know what names all the coordinate systems are called, and if people are using for GSM, what model for the magnetic pole? And there are that's a huge can of worms, actually. But yeah, we need to open it.
You almost took the words right out of my mouth for that.
Oh, sorry.
Yeah. But good. I think I guess great minds think alike. So I would suggest that the space model might be the best available standard reference to follow. And I think CDAS should be making more use of it. And then if it were possible to get Happy or CWeb or DOS2 to give us some token, I think a DOI or maybe a URL for a landing page, or we could get the XML information. I think a DOI would probably be better because that's more likely to be permanent, and then we could just look that up in a catalog somewhere. Then it would be a pretty easy task to leverage that. You go out, fetch the metadata that was specified in the service, and then parse whatever information you need out of that XML, and then apply it to the variables. And then talking about GSM, there are some nuances there that may not be completely captured by space. And going back to this Bepi-Colombo encounter, the researcher was looking at the Themis state files, which have our ephemeris in it. And so we publish both GEI and GSM coordinates in our PDFs. And then this researcher was using an internal tool to convert GEI to GSM. And they were seeing some discrepancies. And then, so we got a help request about it. And it turns out that their internal tool had already updated to the IGRF 13 dipole. And Themis was still using IGRF 12 to co-trans to our GSM positions. So especially if you're looking at some legacy data set that was generated at some point in the past, and it's a GSM coordinates, you may still not know exactly what you're getting. So anyway, that's some food for thought. That's all I have. So if people have questions, I'd be happy to try to answer.
Thank you, Jim.
Can I offer one comment on the coordinate systems?
I had one too.
SPACE tries to take the definitions from the published literature. And I think it would be useful if there's something lacking in those definitions to strengthen them, to make them more accurate maybe or more complete. And as you point out, Jim, there's organizations too that define dipoles and define what these coordinate systems are. I think it's very useful for us to share those common definitions through some mechanism, and SPACE has a pretty good start on it. As you point out, the accuracy of understanding which coordinate system the data is in is very important for a proper interpretation of the data itself too. So,
yeah. And the comment is on the same line. In the frame of the Vespa project, in addition to EP and TAP, we also have been working on the solar system reference frame list. So this includes Earth system and solar frames. This is being done in collaboration with UCLA, with Steve Joy. So we are a bit stalled because too many things to do, but it would be great that we join forces there.
And I like the suggestion also that you had of putting an identifier in the Happy metadata to find more metadata, more detailed information.
I was going to say
a very good suggestion.
That's already there. There's an option you can do for a resource ID. That could be a DOI or a SPACE ID.
Oh, excellent. We should strive to populate that. Yeah,
it's optional because not everybody's coming from the SPACE world, but the DOI, as that becomes more common, that might make it sense to flip that to a required thing that says, well, because Happy is intentionally light.
Yeah.
And but it's got that option to point to further metadata.
Oh, good, good. So you're ahead of the game. So.
I'd like to chime in a little on this too. Two different things. One thing, we'd have to put some sort of subtree under GSM. We don't have a way to capture different models related with GSM.
Good point.
Unless we make the enumeration list just GSM-IGRF12 or something. And the other thing is, this information is not always in the CDF metadata, for instance, from ISTP CDFs. And I've worked to try to fill that gap whenever I can so that the SPACE metadata is actually a superset of information about the data compared to ISTP CDF embedded metadata. So that's one thing where the value has been added to the SPACE documents, and HAPI can take advantage of it.
I'm just going to say one more thing about the coordinate frames, just because the that can of worms is so large, or there's so many worms. I don't know that we'd ever be able to fix that fully, just because some of those published documents about these define the frames. We've had folks try to read those papers and create SPICE frames out of them, and they can't because the paper actually isn't definitive. So it's a very hard problem and requires dedicated experts. So it doesn't say that we couldn't ever do that, but that would have to be, to standardize that at the machine readable level would be a monumental effort.
Well, SPICE is doing that.
Yeah, exactly. So if we, yeah, that's true. If we based it off of SPICE kernels, get this SPICE kernel and with this DOI, and that's the frame, that's a great idea.
Yeah, yeah.
Because it's definitive. It has the mathematical definitive definition that, and I mean, their documentation, no one's going to out-document SPICE.
Right, but our job as information engineers are to be worm wranglers. Yeah, we're trying to herd those worms together. A few of them might run off, but you know,
yeah,
we just have to try and put together the best we can of all this information.
There's always edge cases, but I think the important thing is the people who actually created this data need to be involved with the review process of the metadata that's getting produced, so that these coordinate systems in this case would be, firmly defined. And, other things that are captured as well are things like caveats. And those are important too when you're trying to plot these data or process these data.
I think showing the use case that Jim just showed here, wouldn't it be great if you could load this in and we would do your model transforms for you? That's going to motivate people to say, oh, well, that might motivate people to get the metadata right to enable these kinds of automatic ingestions.
SPICE could help in that area too. I mean, once
Absolutely. They have
kernels you can transform to. Yeah.
Batista's right. That's a definitive way to describe what frame you're using, because it clarifies all those issues of what field model and what, are you doing ecliptic or what mean of date or everything.
But I'm not.
Would it be an IDE recommendation that Space Mission provides SPICE kernels for their reference frames?
I would strongly endorse that.
Yeah, me too. But
well, that was kind of my question: is has the NAIF group produced SPICE kernels for all of the Earth and heliophysics based?
No,
a lot of them, yes.
Not all.
Coordinate systems, maybe, yeah.
Not all, but they are. For instance, on the DESA-led mission, it is done.
Yeah.
Parker Solar Probe uses it. RBSP used it.
Solar Orbiter does it.
Yeah.
A lot of the newer missions do, but I was thinking.
And for instance, I know that the people at CDPP, they have computed kernels for wind for other missions because their 3D view tool is using SPICE kernels inside. So there are also SPICE kernels that have been produced in the community that could be fed back.
We should start archiving them. Well, they're archived at NAIF, are they? Or when groups calculate their own kernels, where are they stored?
Yes, I think so. It's
But you need an official meta kernel to describe what to pull out,
yeah.
because there's way more than what you need.
Yeah.
Right.
Okay, so this is very good discussion. This is a nice working group topic. I propose to go ahead because we are still a bit late.
Baptiste, can I add
Yes.
a quick comment? Yes.
Yes,
In
of course.
what we do is we are using data from SSC Web, and we transform this data in Spice kernel.
Yeah.
And, okay.
Yeah, you should have the NAIF team look that over to make sure, because there's a lot of ways to do that I've tried and don't always get it right.
Well, there were interaction with the people at ISA, I know, at some point, with Mark Costa, I think. So,
like leap seconds and light time things and weird things that.
if we share them globally, yes, of course. At the moment, it exists and it's working well. So
Right.
Yeah. Okay, topic for future collaboration. So, Nicolas, the floor is yours.
You are muted, Nicolas.
Yes, I don't know if you are talking, but we can't hear you.
Is it better?
Yes.
Yes.
So sorry, I'm Nicolas André, so I'm Scientific Director of CDPP. I took over from Vincent Génaud this March, and I will be very happy to meet all of you next year face-to-face during the next meeting. And I will describe here a few things about the tools we develop at CDPP for the use of scientific data by the community. CDPP is a data center. It was established in 1998 from CNES CNRS collaboration for natural plasma data distribution and archiving. It evolved in 2006 into the development of data analysis and visualization tools, including simulations, in order to add science return to the data and make benefit to the users for their daily life in analyzing the data. We have participated in several EU and ESA projects, in particular those oriented toward the definition of standards and of virtual observatory, in particular for numerical simulations. And we also support mission activities. This was the case for the Rosetta Plasma Consortium, but we are also now discussing the same kind of involvement for Solar Orbiter, BP Colombo, and the JUICE missions. And of course, we also try to have our tools used to promote science through publications, but also for educations for the master students and other students. This is the webpage for the data center, www.cdpp.eu, where you can see at the bottom the few tools we have developed these last years. In particular, I will describe the AMDA propagation tool and 3D view tool in the following presentation. So AMDA, for Automated Multi-Dataset Analysis Tool, it's a tool to play with physical parameters, not files. Those data come from various data centers. We replicate data from ESA, Cluster Science Archive, from NASA PDS. We access remotely to data for CDA Web, for also a database of simulation and models. So the data we put in the tool are public or restricted to different communities. They can be exported in companion tools using the SAMP protocol. We can also enable the user to upload their own data into the system. So the data can be accessed via web service using SOAP and REST protocols. And we use the NetCDF data format in order to save all our data. You can register in order to get a user space and to work, but you can also get public access without registration in the tool. So this is a capture screen for our tool. See on the left part the data tree, where you can find all the data we have available for use, in particular the observational and the remote data, either obtained locally or remotely. And also, you can define your own parameters, combining different parameters from different missions and different instruments. And you can have also access to timetables or catalog of events you can play with in order to do your own science within the tool. On the bottom, you can have access various functionalities, in particular visualization functions, data mining function, download upload functions, management of timetables or catalogs, and also some interoperability in order to access remotely to database or data center, in particular for the virtual observatories. So here you can see on the left the various data we have in the tools. They are numerous. We have been able to ingest a lot of data these last years. In particular, we are able to ingest the data as soon as they become available. This was the case for the Parker Solar Probe data illustrated on the top right for the magnetic field and plasma measurements. As soon as they become available, we jump on the data, ingest them in the system, and make them usable for the various users. And I mentioned we, of course, acknowledge the data providers and the source in the system so that the users know about the responsibilities and the caveats in particular. As Daniel Boucon described on Monday, we have this last year ingested a lot of data focusing on the heliospheric space missions, Solar Orbiter, Solar Parker Probe, Stereo, Ulysses, and Helios, since we want our users to take advantage of the multi-spacecraft exploration of the heliosphere and interplanetary medium. We have also focused on old missions for the Earth's magnetosphere, like AMTI, Interball, Freya. We have completed our cluster database from the Cluster Science Archive, and we had added some MMS data in the system. We have also a tool based on a 1D MHD propagation model to propagate solar wind parameters observed at L1 by Wind Omni Discover and propagate them to various planets and spacecraft in the heliosphere in order to predict the status of the solar wind in the vicinity of these objects. So we have developed all that into the database. We recently also looked at machine learning and artificial intelligence in order to help the users to visualize and analyze data in a more sophisticated way. We have started a prototype in order to identify the boundaries of a magnetosphere. It was illustrated on that plot for the induced magnetosphere of Mars. We are able to identify the bow shock, the induced magnetosphere, and the solar wind from the various plasma data obtained around Mars. And we are pursuing that in the coming years in order to add some more capabilities to the system to help the scientific users. We have also, as Vincent Genot described yesterday, developed Happy inside the service. So I'm not describing in detail this. It was done by Vincent, but we are quite happy to have been successful in doing that, and the service is working nicely in the system nowadays. We have another tool called 3D View that Baptiste Secconi just mentioned. It was developed these last 10 years. It took a lot of inspiration from NASA VisBard, for those of you who know. We have been able to develop it with the help of various contractors funded by CNES and also by EU project, in particular Europlanet and IMPEX. This tool enables access to several databases and offer a 3D representation of the data in the model, as well as other capabilities. And the tutorial on the tool is published in a Planetary and Space Science publication by Vincent Genot 3 years ago, where you have full details about it. I just show how these tools was used in order to prepare new missions. In the case of the JUICE missions, ESA was quite happy with the capabilities offered by the tools, where we can combine the orbit of future missions, numerical outputs from numerical simulations, as well as observational data. And we had a press story on that on the ESA website in order to show what we can do with that tool in the context of the JUICE mission for Jupiter, but also for Mars mission, together with our collaborator Ronan Modolo in Latmos, who developed numerical simulations. We have a third tool, the propagation tool, which enable to propagate radially perturbations in the solar wind, CME, CIR, and ACP, and predict their time arrival at various objects and planets. And this tool will surely prove very useful in the context of the heliospheric observers, Solar Orbiter, Parker Solar Probe, and Bepi Colombo, who are getting new data nowadays. I just show you here how the tool is also connected to MEDOC, so the French solar data center, also to our AMDA tool, and also to a database of Hubble Space Telescope UV auroral observations at Jupiter and Saturn. So we have developed and enriched the tool with various interfaces to access remotely to all of the following databases and tools. We have developed a new tool also to do run on requests. This was something new during the Europlanet project this last year, where you can run some magnetosphere ionosphere coupling models, store the simulation outputs, and use them, visualize them using the SAM protocol in our tools. This was, in a sense, a small attempt to do something similar to CCMC in the States with a much more modest approach and objective. But we succeeded in doing that this last year, and we hope to develop it furthermore in the future. So based on the use of the 1D MHD propagation model, using observational input at Earth and propagated towards planets, spacecraft, and other objects in the solar system, we developed a HelioPropa tool in order to predict the status of the solar wind and the planets, in particular Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus, and to comets. And we hope to use that tool in order to predict the status of the solar wind using inputs not only at Earth, but only from Solar Orbiter, Parker Solar Probe, or possibly Bepi Colombo, in order to refine the prediction and the properties of the solar wind at various planets, offering to our users some virtual space monitors to combine the predicted observations together with the real observational observation by spacecraft around object, in order to obtain the global context of the solar wind planet interactions. And this was also proposed through our efforts to participate to the ESA Space Situational Awareness Program, where a few of our tools, the propagation tool, the AMDA tool, and the HelioPropa tool, were proposed to the data center built in Europe in order to do space weather and planetary space weather in particular. So in conclusions, we have developed what we call a community infrastructure. Our tools are used by a wide community of scientists. We rely also on collaborations with the data centers, the data providers, and the feedback from users. We are reviewed regularly by a user committee of 10-15 scientists, and we have about 10-15 publications analyzing the services and the tools per year, which is quite rewarding for the technical and scientific teams behind our tools, which are about 5 to 8 persons. And I guess to summarize, here it's the three main tools, AMDA, 3D View, and the propagation tool, how they fit with ID in terms of protocols, data models, web service, formats, and a license. And I will end up with that slide on the screen. So thank you very much for your attention.
Thank you, Nicolas. So any questions for Nicolas?
Just a precision from my side, the API is no longer a prototype now. You can for AMDA on the second column.
Good.
Yeah, just a remark on the Solar Orbiter. What's available at AMDA is the MAC data. The past data are not public, and they are not public on the Solar Orbiter yet. They are coming up at the end of November. So because people are eager to get their hands on this data, just to say that they are restricted to the past people, proton alpha sensor people at IRAP, as far as I know.
Yes, this is true. We are able to have data both public and restricted to particular communities, and this is still the case for the Solar Orbiter past data. But hopefully soon they will be some of them will be publicly released, and we will ingest them and offer them to the community.
Yeah, thank you.
Can I ask a question or make a comment?
Yes,
sure.
It's Marsha. So I have been hearing there are several, entities are developing CCMC type capabilities, and on the other hand, we currently start remodeling significantly, modernizing our runs on request capability. So it's a good opportunity somehow, maybe establish a working group, but somehow to look and review the best practices and maybe build a whole network of simulation services so we can, for example, cross links or request runs on different, centers and visualize them. And it's if we, for example, our next generation is built completely on space, and we're trying, to implement annexo impacts. So that is, I think, if people start building this type of capability, it's better to build, worldwide network of simulation services. That's my suggestion.
Yeah, it would be nice. In particular, in Europe, we have the Europlanet, a new Europlanet program for the community that is running, and we have some ambition to go towards this kind of infrastructure and facilities. So we would be very happy to interact and follow things within the community.
Yeah, and again, if you're now defining standards, the way how users interact with, back end, and eventually make it so your users can request CCMC runs and CCMC users can, through API request certain runs. And it is here, I know that there is virtual modeling center. It's something to discuss here. I think that, IHDEA is in the position actually to become as a hub for this type of activity. Yeah. Because, the runs on request system have been developed 20 years ago as it is now. Some scripts have been written by myself. So it's not using this, and it has been working well, it did a job. But now we're redesigning it using new approaches. And Maxim Petrenko, he's leading this. We hired a few software developers that have been here. So we're redesigning it, but we are willing to look and make it more compatible with others. And I think you guys just start working on this. So again, it's just somewhat idea maybe for the working teams that we will start establishing tomorrow. Thank you.
Yes. Any other question?
No, I think it's something to discuss tomorrow for the working group.
Okay, so let's go to the next one.
Can I hop in? I think you skipped over me. Thanks. So I haven't tried to share my screen yet.
Oh yes, I forgot. Oh, sorry. Yeah, I'm keeping forgetting people.
Let's see if this works.
Okay.
I've not tried sharing, so can you all see my screen okay? Is my screen?
Yeah.
Yes.
Yeah. Yeah. We can see it.
All right. So I'll be quick. So I was just going to talk about where Autoplot is and a couple of Java libraries that we have for accessing HAPI and doing some science processing. And I didn't have an author list on the sign up for this, and I felt bad about that, but I couldn't figure out how to update it. So this has contributions from many people. So I'll overview Autoplot for this last year, changes that have happened. I did a more introductory talk of Autoplot if you're not familiar with it and you're interested in learning more about it at last year's IDEA meeting. And this is a link to the site. And I'll introduce these two libraries that could be useful in other Java systems as well. So just quickly, I'll describe what Autoplot is. It's a Java application for display of data, a client that runs on the scientist's computer for displaying data from many different sources. Data sources are identified by Autoplot URIs. So they would type in this Autoplot URI into this address bar, and the data would be loaded automatically. It's then displayed as spectrograms, line plots, or whatever, depending on what the structure of the data is. And typically, the scientist isn't going to have to produce these URIs. They could be file and then add plots, going to a special GUI for the happy servers that know about what happy servers are out there, and it would negotiate with them and show what variables they're or what data sets they're providing. And once all the data is loaded, you can click on the data using the DOS2 library and look at a slice of the data, for example, or crosshair, those kind of things. And then there's also the scripting language Jython, which is the Java implementation of Python, is provided for creating science workflows. So I can write, if we need to do a particular analysis, I can write a script that makes it easy to do that analysis. Actually, I need to have two slides here because I'm going to talk about aggregation throughout this. And that's basically where, normally you'd point Autoplot at a remote file sitting on a website, and it would download that file behind the scenes and then display the data within. You can also use aggregation, which is you give it this template string for how to create the thing, $Y for year and so on and so forth, $V for the version, it picks the best version. And you give it a time range, it'll download the files needed and display them together as an aggregation is what I call them. So new this year, Chris Piker's provided a .exe release for Java. Java used this web start mechanism for basically as long as I've been working with it since early 2000s, where you just click and the application would come up, and as the internet's gotten more and more security conscious, that's gotten more difficult to use, and it's been more attractive to have just native installers there. So we have a .dmg for Macintoshes that you can download, and that'll install the application on your machine, or a Windows.exe similarly will put that onto your machine. I was going to drop support for the web start for those that are using it, but there's a couple of groups that they really need to have access to that, and even though Oracle has dropped support for web start, it will continue with the OpenJDK to be available. I work with the CDF web group at NASA quite a bit. CDF files are kind of the first format for Autoplot. And what's new this year is, you could always click on a CDF file and it would show you what was inside. Now you can select multiple quantities and hit plot, and you'll look at that. You can also say, use this quantity for X, use this one for Y, and this one for Z, and then I'll look at color plots. And that's really mostly just for efficiency. Before you do that, you kind of have to piece things together with a script. This lets you do it all in one shot, and you can load all that data at once. And likewise, when you can load data, typically you can export data too, and you can do the same thing when exporting CDFs. One of the biggest problems that I have with Java and Autoplot and the big data that we work with is to memory limitations. So on a 32-bit machine, you only have access to about 1 gigabyte of memory. Now, the CDF reader that I use, provided by NonLol, does smart things with memory, and oftentimes I can read outside of Java's memory and access up to 2 gigabytes of memory. But there are cases where I can't do that. And we've been working a lot this last year to make sure that Autoplot can get into those larger data sets. And a big question that I have a lot lately is, I still support these 32-bit machines, even though there aren't so many 32-bit machines running around anymore. And it would be nice to just drop that and essentially just let the people use 8 gigabytes or whatever and not have to run into these problems. At the Plasma Wave Group, where I work at the University of Iowa, we have this waveform scheme, which is an efficient way of storing waveform data. You can imagine you have a measurement for every time tag, and just as an illustration, back when there were epoch 16, we would have a 1 byte data value for every 16 bytes of time value. That's a lot more inefficient than it is with epoch 16s, but it's still fairly inefficient. So we store things in these 2D arrays where we have time for one dimension and we have time offset for the other dimension. You have sort of wave packets that you can access. And that's becoming kind of more of an official format that CDAW recognizes, and is kind of going through and looking at what groups are producing data sets that look like that. There's 5 or 6 of them that are. And likewise, there's more and more products coming out as NetCDF being served by the CDAW group, and I want to have support for that works just like the CDF support does. Also new this year is support for IDL save files. You could actually write IDL save files in Autoplot for quite a while, but you have not been able to read. And there's essentially an open source specification of what an IDL save file is. And I've used that specification to write a reader for it as well. Python's able to read these. So clearly there's a desire to have this functionality. And as soon as I told people that this was available, it's surprising how many people said, oh, I can get into these data products now, and used it immediately. And I was curious, I ran a search on my machine for IDL save sets, and I found this is one that was in SpeedOS, one down inside a bit, and I was able to open that up no problem. Autoplot's had this basic mode for quite a while where you could flip this expert switch over to a basic mode and it would kind of simplify the GUI. And it hasn't gotten a lot of use, and we've tried to make it more useful. And the goal here is to lock down, Autoplot's a very flexible application, so we're trying to lock it down and make it do a particular science task. So that you could hand Autoplot and an address to a scientist, and they can load that address, and it would go. So they can click on, or they can drag this VGPWS link, that's the Voyager spacecraft, our data on Voyager, drag it and drop it onto Autoplot here, and up comes the application. It turns it into basic mode. They can flip around in time, but they can't add additional data sets and things like that to make it essentially to make it so that they won't push the button and get into a strange state. You hand it to people that are not familiar with the software, and they should be able to operate just fine. Documentation is an ongoing thing, and not much to say there. CSVs have been a problem in Autoplot for quite a while, where we have a specialized code that we use to read CSV files, and that's because you can do strange things. CSV is a little bit like XML, where you really shouldn't be writing a parser. If you have a quoted field and have a new line, for example, you don't have to pay attention to the new line. That's all one field. So to implement that, I had used years ago a CSV third-party library to read those in. And then all the other ASCII files that I would read in using this generic ASCII reader on the right. So with COVID, I had kind of a nice long period that I could just finally knock this out and make sure that our ASCII reader could read any CDF or any CSV file as it could before. And now when you're reading CSV files, you'll get just the same interface. But if you have people who are using CSV files to produce and they still have problems, that may be why, and please let me know. I have another talk that's posted on the website for this meeting that talks about these URI templates. So Autoplot's always had this mechanism to load multiple files from multiple templates. In about 2015 or so, we came up with a formal specification for that, me and a couple other groups, John Vandergriff and Bobby Candy, to describe what these URI templates should look like so that we could describe all the data sets we need to describe. And we came up with that spec, but there was never a reference library for it. And I've written a independent Java library that can be used for that task. And it's mature, should be quite robust, and it's kind of long overdue. So that I expect that if you're writing Java, you should take a look at that, because that might be useful if you're trying to identify, you have a pile of files with particular names. This lets you find them. And likewise, if you have an individual file and you want to know what the time range is that it corresponds to, it does that for you. So this is the link for that show. And then Autoplot kind of has been involved with Happy since the beginning, and its Happy reader, its Happy client is, built into Autoplot and it uses all sorts of the Autoplot internals. So it was not useful externally unless you were willing to bring in all of Autoplot. So now I've extracted, so there's just a nice simple Happy client that's available. This one does nice things like it'll stream the data to you so you can get it record by record, so you're not limited by memory limitations, or it conveniently will put it all together into one giant 2D array or whatever form it is. And the other feature that it provides is we define client-side caching. So with Happy, you can imagine that scientists tend to look at the same data again and again and again as they return to their analysis. You don't want it going off and reading the data over and over again. It's because you're paying the cost of transporting it over the internet. So we have a caching mechanism for it where Autoplot can say, okay, I've downloaded this data set for this day already. Has the result changed, since the last time I downloaded it? And it'll manage keeping that data set or that local cache up to date. So I think that's all I wanted to talk about. And thanks, and let me know if you have any questions.
Thank you, Jeremy. So since it's a little past 4, I propose to have our minute of silence, as I said earlier today. So let's start now. Thank you all for doing this. Sorry, Jeremy, it's a bit of. No, that's fine. It's cutting a little bit your effects, probably. So, any questions for Jeremy now?
You have the separate Java libraries on GitHub somewhere?
Yeah, those are on our Happy site. I think I have. If I didn't put the reference up there, I'll make sure it's available to people. But GitHub/Happy server. Happy
Okay.
server.
And the URI templates too, or that's its own thing?
That's down there too. Just convenient place to put it. So.
Okay.
So the URI template is the same as what is the same specification as the one that is defined on tsds.org or something like that?
Yes, exactly.
Okay.
That specification has been moved over to the Happy area, the Happy server area in GitHub.
Okay.
As well. Yeah, that is the specification.
Okay. Yeah, we should probably have on the ID website this kind of these specifications that we are using and put links to those at some point.
Yeah, I mean, it's not a terribly difficult problem to solve, but if we're all solving it the same way, there's benefit to that.
Yeah, yeah. Okay. Well, Autoplot is so much used. So I'll check this drag and drop thing of the script and yeah. And,
that would be nice. Yeah, try that Voyager
and the scatter plot too, because I tried before and that was a mess. If you made it easier, that's good. Okay. Okay, so I think we had a lot of discussion during the talks. So unless there is a more generic discussion on the tools now, we can go to the Python session.
You don't want to present your tool?
Well, we are late. There is a video online.
Okay.
And we will discuss during the working groups if needed. Now it's I want to save a little bit of time. If not, we are going to be very late.
Thanks.
Was that the EPN tap then?
The presentation, no, the presentation was on Mazer, which includes EPN tap, but EPN tap was presented shortly yesterday. So this is Jack speaking, is it? Who was talking?
That was Lee, sorry.
Ah, okay, sorry.
Yeah.
The Mazer project, I can say in a few words, it's a toolbox for low-frequency radio astronomy, which is a type of data that is not so easy to use. And the spectrograms are remote sensing, not in situ, so it's really a different beast in space physics. So we are proposing tools using autoplot, DAS2, and also run on demand for simulations. So all this is presenting in the video, and we will discuss that during the working groups, I guess. Okay, so let's go to the Python session, and Julie is going to give, I'm sure, a very nice talk on the Python heliophysics community.
Yeah. Let's see. How does one share their screen? Unlock. Allow.
Share button at the bottom.
Yeah. Until. Okay. Oh. Why is it doing that? Sorry. I didn't know I had to do this before. System will not be able to record the content. Yeah, later. That's fine. Okay. Sorry, that's weird. It's making me like leave the meeting before I can share it. I was not expecting that. 1 second.
Okay.
Are we recording this? Because I don't see the recording indicator.
Yeah, it is.
Maybe I just missed that.
I see it here.
It's at the top right.
Top right, yes.
There is a red cycle.
Ah, yes, it is. Thank you.
Hey, Baptiste, while we're waiting,
Okay,
can we add one little item for tomorrow discussion about the IHDEA website? Because there are a couple of things that were mentioned. It'd be nice to have.
Yeah.
Hey, sorry about that. That was being really weird and made me quit before I could share. Anyway,
Now we can see.
what's in my screen? Swap displays.
Yeah.
That would be better. Perfect. All right. Hey, everyone. I'm Julie Barnum. I work at the Laboratory for Atmospheric and Space Physics at SU Boulder in beautiful, albeit smoky currently, Colorado. It's good to meet everyone. There's a lot of new names and faces that I'm not familiar with. So hello. In any case, today I'll be giving more of an overview presentation than what you've seen from all the other participants about the Python and heliophysics community, PyHC. So when PyHC formed back in 2018, we were based on this specific initiative wherein we wanted to help coordinate Python development efforts across the heliophysics community. We wanted to improve communication between developers in that community to develop and apply standards to their code, to reduce duplication of effort. So there's a lot of reinventing the wheel going on, to increase interoperability, support various widely used libraries, and encourage new development, especially as pertains to collaboration between the various developers in heliophysics. So some initial goals we had when we started, sorry, it keeps going, was that we wanted to establish a standard set of libraries to use for development, as opposed to having a bunch of disparate efforts going on and everyone kind of doing the same thing, but just slightly differently. We wanted to establish code standards and ensure that everyone in our community met them, document best practices and recommendations from the community on our website and so forth, to publicize existing code so new projects wouldn't have to reinvent the wheel, they'd be aware of what's out there. We wanted to identify community needs for new development and help facilitate the ability to do that and help collaboration therein. And we wanted to continue to evaluate proposals for new development projects and find opportunities for our projects in PyHC to get funding. So we've done a pretty good job of addressing all of our initial goals, I think. We've identified several packages that are relevant to PyHC. On our PyHC website, we list all the PyHC packages we've accepted. And in those packages, we identified 5 core packages, which have a wide range of functionality in their area and conform to the standards that we've set. So as I mentioned, we established a set of PyHC standards. Those were based on the AstroPy standards, as we felt that they were very mature, well developed, and fit what we wanted for our community. We picked those out, or selected those fall 2019 meeting, I believe. And in any case, we're having projects grade their development according to those standards that we've developed based on AstroPy. We're continuously reaching out to relevant projects to bring into the community, have them present at telecons and at our PyHC specific meetings, or even give them the opportunity to hop in on some of the AGU poster sessions that we've hosted. Yeah, and we've also done what we can, finding funding opportunities for our projects. The first NASA Roses PyHC IHDEA awards are wrapping up now, and we have a second round of proposals under selection as I speak. I don't think we'll be able to announce that by our fall meeting, which is coming up soon, but that's a thing that's happening. So I mentioned that we had drafted standards.
Actually, we should be able to announce them during the fall meeting.
Oh, perfect. Awesome. That'll be great.
I'm having a meeting about that soon.
Perfect. Great to hear. So yeah, come to our fall meeting and you'll hear about that then. So like I mentioned, we had set forward some PyHC standards, I guess those at the fall 2018 meeting, based on those AstroPy standards. And I won't go into detail on all of these. You can find our standards document up on our website. But we have 15 different standards that we agreed upon and thought really fit what we want for our community. And it's based a lot in having open source development, making sure your code's well documented and tested, that you're using Python 3 and so forth, and that you follow the code of conduct that we've put forward. I just wanted to give a shout out to Sean Polson, who we've hired to fill the PyHC developer role. So we decided back at the fall 2019 meeting that we could really benefit in PyHC from having a PyHC specific developer who would serve as the science software technical point of contact, help maintain and implement compliance criteria for our projects, and make sure the projects are meeting our standards and are grading their code to see if they meet our standards, and who would help with various other tasks, helping maintain the website, assisting in planning and organizing our meetings, and so forth. And since being hired, Sean has done an excellent job, immediately tackled a bunch of issues that we've had backlogged for a bit in our GitHub repo for our website and so forth. So wrapping up, plans that we have for the upcoming year. So we want to continue to maintain and update our PyHC website. The link is there. Please feel free to go visit it and learn more about the PyHC group. We want to continue working on bringing all of the PyHC projects up to date with the standards that we set forth back in that PyHC meeting we had in 2018. We have telecons that we hold every 2 to 3 weeks to discuss various topics that are of interest to our group. Currently, over the next 4 weeks, we're going to be having our fall meeting, so the schedule is going to be a little different than usual. But if you go to the PyHC website, we list all the various times for our meetings in a Google Calendar doc. So yeah, and we'll be holding our fall 2020 meeting here soon. It's a completely virtual meeting, as this one is. It'll be held on Zoom instead of WebEx. So that starts next Monday and will end November 16th. So we're going to be having 2 sessions a week. One session every Monday of the fall meeting, and then on the Thursdays we'll have either an unconference session, a hackathon session, or more discussion. So other plans are to also plan a spring 2021 meeting. Probably will also be virtual, but if it can be in person, we would hope to do it in Boulder or in Boston, but likely virtual again. We'll also have a session at AGU in December that I wanted to point out. It's the Python application development for solar and space physics. And it'll be on the Tuesday, December 8th of AGU for like 16 hours or so. I think poster submissions are allowed to pick like a 2-hour range where they're available to present so that they're not up in the middle of the night. But in any case, we have 11 posters that we have submitted for that session, of which I think 2 are students, so that's exciting. But yeah, that's what I have as an overview of PyHC for you guys. If anyone has any general questions about the community, happy to field those. If not, we've got a few projects coming up that are part of the community that are going to be presenting and showing you their work.
Thank you, Julie.
Yeah.
So I'm sure there are questions. So did you plan to convene, to chair the session during the full, the AGU session from 4 to 9 p.m.?
That's a great question. You know, they haven't told me exactly what I have to do for that,
Yeah,
but I imagine I'm allowed to pick a specific time or split it with other chairs.
Yeah.
I
have the same problem, and I'm co-chairing this session with you. And yeah. To me, it's 1 p.m. to 6 a.m. the next day. So it's just crazy.
Yeah, I forget. We're -6 right now, so that's 10. Maybe to start at 9 once the time changes until like the morning.
Anyways, so.
Yes, Julie, do you have a sense of the size of your community? How many people are attending this kind of session or meetings?
So our telecons usually, it ranges in size, but anywhere from like 20 to 40 people I've seen on our biweekly telecons. At our last virtual meeting, we had upwards of around 50, maybe 60 people at the highest who were in attendance at that. But if you go by our mailing list, there are 100 people subscribed to it.
Okay.
Yeah.
Thanks.
Yeah. I'll go ahead and stop sharing.
So you said I had one question on the so when somebody is publishing a library on the Python the Python heliophysics website, there are a few criteria that must be met. So I think is it a self-evaluation or is it something that is checked and reviewed?
So currently it's a self-evaluation process. We wanted to keep it pretty low-key and low barrier of entry to get projects to evaluate themselves and come up to compliance with our standards. So, and the instructions for doing that are listed on our website under the projects tab. But yeah, it's pretty straightforward. Basically, you're just grading your code based on our standards and then submitting a pull request on GitHub, and someone will review it and make sure, you know, looks good. You're not lying.
And there was also a project I remember about having tutorials or Jupyter notebooks showcasing how to use the tools. Is it still planned or?
That's a good question. It's something that hasn't come up in a bit, but I can certainly bring it up.
That was really a good idea,
Sean.
I think. But,
yeah.
I think a lot of these things are in principle sitting in the background waiting to be done, but there's fairly limited resource of people to do them.
No, but that is a good point. And I mean, we did hire Sean recently back in June. So I can bring it up with him and see when he might have time to start considering that and encouraging the community to participate in it. Yeah.
So I'm curious, oftentimes Python codes are sort of wrappers around C codes. That's fine, I assume? You accept libraries that are natively written that have a Python interface?
I would think so. I'm not sure how many of our libraries actually do that, but
or do you guys
SpacePy, for example, the reader is
typical example.
Yeah, right.
Underneath, and it makes it more efficient, but it's a little bit more overhead to get it in.
And I know Chris isn't on, but I mean they have a native DOS2 stream reader, and I wonder how that's accepted by your community.
As long as it's wrapped with Python, I think we would at least consider it. But
I've got an open question about. I mean, at IHDEA we had this discussion this morning about how to measure the community using Python compared to other tools. And we were considering, for instance, in our tab server to add some kind of parameter where you could put like an optional parameter, but that could be included in these Python libraries, saying HelioPy or SunPy or things like that, that would allow us to know how much data is downloaded through these Python libraries. And we would, of course, feed back to the people coding these libraries that where there have been so many terabytes downloaded through HelioPy or SunPy or things like that. It's interesting for us and it's interesting for you. On our side, if we see that most of the data download comes from these Python libraries, then we would put more effort, towards the different tools we provide to the community, saying the GUI or the tab server, or I don't know if you would consider that a good idea. It's more of an open question.
So Arnaud, I might suggest that the client can identify themselves. Usually, it says what type of browser they are. When Autoplot connects to things, it says that it's Autoplot connecting, so that servers understand that there's this product out there that's talking to their server. So I'd suggest
it's an agent tag in the first request.
Of course, we can of course distinguish between a GUI and a tab server, but if the tab server comes from a normal Python code, or comes from an individual Python code, or from a hard-coded request from HelioPy, that with this extra parameter we could monitor and provide feedback. It's not only useful on our side.
Well, I would suggest that the Python codes would put that request header in their request.
Yes, not to change the request of users,
it's the header.
No code change. It's more of an extra parameter hard-coded in these Python libraries.
Well, either place it's going to require a change on the Python code, right?
Yeah.
On the Python code in the Python libraries, but in the import module of the Python libraries, but not on the user side.
Yeah, it's just an extra line to put in the header you sent, the HTTP header that you sent during the request. So it's not
an extra parameter.
No.
It's not to include it in the HTTP header. It's about just let's say one more parameter on the HTTP request. I mean, where you say, okay, I mean, this is my servlet, and then the parameters like download product dataset ID, and then it will be something like origin HelioPy. I mean,
that would work
just,
too.
Yeah, and it's it's only adding 2 words to the tab.
And it would work even if the tab server doesn't understand this keyword.
Yes, of course.
Okay.
Because if it's not a mandatory keyword.
Okay.
It's just an optional keyword that could be added in the Python libraries.
And why would we not use the HTTP header? Because this is standard.
Yes, but it's not. I mean, if for the users or the ones who has to implement it, it may be more complicated. No, you need to know more. What is an HTTP request? I mean, if you just are coding on Python and then you just write the line and you have the example, you take it, you copy, and then you only change the dataset name.
But you still need
time.
Okay, yeah, maybe.
Back for how to do it. You should just play with it.
But both things are possible, yes.
Yeah.
So,
discuss that, yeah.
Arnaud, so this is a good idea. At the VSO, we already know that the IDL VSO client and the Python VSO clients have about the same amount of traffic. So it really does guide the development of the VSO. That we know we have to support the VSO, the Python client, and for the VSO. So that's where the effort goes: the IDL client and the Python client. But we can measure that.
Yeah, and this way we cannot measure at the moment.
Okay.
The solar people, Jack, correct me here, that you also did a survey of who uses what analysis tools, right? And it came out sort of what you'd expect, but the younger people using more Python, etc. But it was a very interesting survey.
Yes, that's correct. That is published, I believe, in Solar Physics now. So yeah, modulo the bias, which is the only people who reply to surveys are the people who reply to surveys, and they have they normally have an interest. So given that, we came to some conclusions. I should post the link in the chat to that paper.
Yeah.
I just posted it there.
Thanks.
There you go. Thank you.
Thanks.
Well, Laura, I think it's your turn. Anyway.
Yeah, it's a good leeway in, right?
Hello, by the way.
Hello. Hi, everyone. Can you see my screen?
Yes.
Yes. So, hello, everyone. My name is Laura, and I'm a postdoc at NASA Goddard. And I'm here to talk about the SunPy package today. And I'm talking on behalf of the entire SunPy community, because, of course, it's not just a one-person effort, it's an entire community. So this is going to be quite a high-level talk, but we can talk about more specific things of SunPy if we want to down the line. So I'm just going to give an introduction to SunPy, where we kind of are, what the status of SunPy is, some of the main key features we now have with this new stable release of SunPy, and kind of the roadmap for the future, where we want to kind of go with SunPy. So just to begin, for somebody that does not know what SunPy is a community-developed, free, and open source software package for solar physics. And the SunPy project essentially tries to facilitate the goals of the SunPy package. And it does this by facilitating and promoting the use and development of several community-led free and open source data analysis software packages for solar physics. And these two main goals can kind of be divided into functionality and cultural. So from a functionality point of view, SunPy wants to be able to provide Python tools specific to solar data analysis. So this may include like finding data, downloading data, containing data in different data containers, and loading this data in from different kind of file types that are used in solar physics. And in this way, this then opens the door to the whole ecosystem of scientific Python, whether you're doing kind of machine learning, statistical analysis, visualization. And as we talked a bit before today, the idea of SunPy is to kind of work on like science ready data. So it's not doing kind of prepping routines. It's looking at science at level 2 data that you already have. So instrument teams would already provide kind of the calibrated files. And kind of one of the main functional goals of SunPy and kind of is not to kind of reinvent the wheel, is to try to leverage a lot of the code that's out there and a lot of the mature and maintained software that is available already for such things like AstroPy. And as well as SunPy Core, which is kind of the generic package which is used by a lot of solar physicists, we want to support kind of affiliated packages, which would be affiliated with the SunPy Core library and depend on it. So an example of this would be kind of an instrument-specific library, such as AIAPy, which would be then a SunPy affiliated library. So kind of more specific packages that are kind of in a niche within solar physics. And as well as all these functional goals to provide from kind of a software package, we also want to develop kind of a cultural environment, kind of an open source community that's both open source development and open source code. So it's based on Python, which is non-proprietary. And we really want it to be inclusive of everyone. So anyone can contribute, whether that be through code, be through feature requests, be like issuing bugs or things like that. And again, as well as developing this community, there's no point in kind of reinventing the wheel. So we don't want to have isolated scientists writing their own software that are essentially doing the same thing. We want to coordinate development within the community of solar physics to kind of get kind of best scientific return we can. We also want to have a set of standards. So this is kind of a good package. So it both has code testing and code review to kind of have a sustainable package, which can work all the time, essentially. We also want to have version control. And this is really important for any type of kind of scientific use of SunPy. So if you want to do something, if you did something in SunPy 0.5, you want to be able to go back and replicate what somebody did in a paper. So it's really important to have a version control ideology within SunPy. And again, we want to standardize and we want to standardize documentation and make it discoverable. And this goes back to making it kind of open source and for people to be able to kind of find it and be able to use it. So that's kind of an overview of what SunPy is. And how can one contribute to SunPy? And what does this look like? So I said that anyone can contribute. We're really trying to be an open source, welcoming community. And it doesn't have to just be like providing code. As a community, we need to know what the community wants. So we need to know what features that people are requesting in SunPy. We want to know when there's a problem in SunPy, and we want to have feedback and suggestions. So we don't just want to be developers developing this package isolated. We want to talk to the community and make it something useful for the entire solar physics community. However, if you do want to provide code, we have certain guidelines in place to make sure that the code is kind of up to standard and we have high quality code base. So every contribution of code has to go through these 4 steps of standards. So kind of the style guide, so it must conform to kind of the widely used style guides such as PEP 8. It has to, every kind of new contribution has to have associated documentation, whether that be what the function does, and if it's a large enough thing, maybe you have an example written to put in our example gallery. Again, we want to have a continuous development of the SunPy package. So we, of course, have unit tests to make sure that the contributed code doesn't break anything. And we also want to make sure that the contributed code is within the scope of what SunPy core wants. So is it kind of what the kind of goals of SunPy is, or is this the roadmap we're going down, or is it too specific? So we kind of, when you contribute code, these are kind of the standards we go through, and it is a two-way conversation. So it would be a PR on our GitHub account. And for newcomers, we really would like, we have a lot of kind of help is given by the other software developers, or the community developers. So where is SunPy now? So the project, just to give some backstory, the project was officially founded in 2014, but kind of the SunPy core package was kind of began in 2011, which is almost over 9 years ago now. And in the last year, there's been kind of a load of new things that have happened with SunPy, which is great. We've had our first stable release, which happened late last year. And then we've had now SunPy 2.0, which is in the summer, and we are now in SunPy 2.0.3. And as of our first stable release, we now have a release schedule. So before it was kind of ad hoc when we were kind of found that it was together enough, we released a new version, but now we actually have a release schedule. And as of SunPy 1.0, we have around 50,000 lines of code. So this includes comments and documentation. And we had 134 unique contributors, which is kind of nice from the solar community. We also published 2 papers based on the code. So we have one in the Astrophysical Journal, and then we also have one in the Journal of Open Source Software, where the software, or the core package itself, was reviewed. So you can check both of these papers out here. And this is a nice snapshot of kind of the current status of SunPy as it kind of grew from beginning to 1.0. So we can see this is the lines of code in thousands over the years. So we can see it's increasing. And there's this big drop just before 1.0. And this was just essentially a major tidy up before we had a stable release. If we look at the cumulative contributions, we can see it's steadily growing as you would expect. And this is the number of commits to the GitHub repo versus the number of contributors. So we can see this is quite steep, meaning that there are kind of a few key developers that are developing the majority of the code. But if we want SunPy to be stable and to keep growing forward, we really need to make this kind of more flat. So we want to have more contributors contributing more code, essentially. So we're not depending on 1 or 2 people to develop the main package of SunPy. So the highlights of SunPy 2.0 and from 1.0 from our stable release, we have a major cleanup, as I said. So the code stack's kind of nice. There's not a lot of legacy code lying around anymore. We have really nice improved download capabilities that is based on the package PAR5, which allows like asynchronous parallel downloads. I think one of the nicest thing is kind of improved coordinates functionality. So we have an awful lot of some specific coordinate transformation functionality now that is based upon AstroPy. And throughout the whole SunPy core package, we now adopt to some AstroPy time. So that's kind of a standard that we have now. We also have a logging system. So instead of printing out all errors or bugs, we can now log these to a file. I'll just give a really quick overview then of the kind of the core functionality that we have within SunPy, which is the retrieving the data, kind of loading in and containing the data. And then I'll give a nice example of the coordinate transformation stack that we now have. So first of all, our data retriever. So this is kind of the main thing you might want to do is you want to get access to the data. So FIDO is a kind of a unified interface for searching and fetching solar physics data, irrespective of the underlying client of which the data is obtained. So for example, you can use FIDO to query the VSO, to query the JSOC, to query individual HTTPS clients for basic for different instruments. And here's just an example. So we can import FIDO, and then we can search by different attributes for different data. So we can search by time, we can search by instrument, you can also search by wavelength, and there are many different other attributes. And then you can fetch it. So it's kind of a unified interface. It doesn't matter. The user doesn't really need to know where the data necessarily is coming from, but it's a nice kind of way to do this. So you can query kind of from different clients over the same time range or the same wavelength. And then once you get this data, SunPy has two main data containers to load in the data. And these two main data containers are kind of the most used, maybe perhaps, in solar physics. So this is both time series and map. So time series is, as you would expect, 1D temporal data. And our time series object within SunPy allows you to kind of contain the data, the times, and all the metadata associated with the time series. And then we have different functionality available within it to be able to truncate, to concatenate, to resample, and things like that. And second of all, we have our map, which is a 2D coordinate-aware image data. So we have lots of different nice images of the sun and many, many different wavelengths. So map is a data container that kind of takes into consideration the WCS of the image and kind of can plot it then with WCS axis within AstroPy, which is really nice. So these are our two main data containers. And these are kind of standard and consistent. So it can load in the data irrespective of the data type once we kind of, if SunPy can do that. So for example, you might have a FITS file or a CVS file or a CSV file or something like that. And then finally, this is just a nice overview of the coordinate subpackage that we now have. And SunPy coordinates essentially is there to provide support for representing and transforming coordinates in SunPy. So this is an overview of what all the frames that SunPy support. So you have all of the sun-centric frames, such as helioprojective Cartesian. We have helioprojective Stonyhurst, and this is all built upon AstroPy, the AstroPy coordinate stack. So this allows us then to easily transform between solar-specific coordinates into terrestrial coordinates, and we also have added in some Earth-centric coordinates as well. And why this is really important is that now going forward, if we have lots of different observations that maybe we want to plot in different coordinate systems, this is really now easily done within SunPy and to transform between them all. And to give you a nice example of this, on the left-hand panel here, we have an image of Core 2 from Stereo A. And this is a coronagraph image, so we can see that the sun's corona here. And all these white dots are essentially the positions of stars taken from the Gaia catalog. So we can get the positions of the stars in the Gaia catalog in whatever coordinate system they're in, and we can transform them very easily into the helioprojective coordinates and then overplot it on the Core 2 map. And similarly, to the right here, we have an AIA 171 image and overplotted the coordinates of a magnetic field extrapolation. And below here we have, this is a plot of AIA 1600 when Venus was transiting the sun. So we can guess the position of Venus from ephemeris, something like that, and then plot it in helioprojective coordinates. Very nice and easy. And then another thing that might be really of interest is to try to look at the sun in two different fields of view. So here's an example looking at the same active region with both AIA and stereo, which we can see are looking at the sun from two different points of view. So we can find an active region of the sun, for example, in AIA. We can transform what that would look like in stereo and plot a box around it, and then define different loops out and pull out those coordinate systems. And this is really important kind of moving forward with new observations with Solar Orbiter and Parker Solar Probe, which will look in vastly different coordinate systems. So we want to be able to, if we're doing if you're doing a study looking at these two different instruments, for example, you want to be able to kind of hone in on different active regions that you're looking at and take into account the different points of view. And just to kind of, if you're interested in learning more, we're trying to do a lot at the moment to increase our documentation and make it as accessible as we can, as I said, and discoverable. So here's just an example of our SunPy documentation. So we have a nice user guide for kind of getting set up and the different kind of functions that are available within SunPy. And we also have an extensive example gallery showing all the different functionality within SunPy, whatever you might want to do. And we would ask you if you have something that you would like to see within this example gallery, please raise an issue on the GitHub and ask for this. Or, of course, we would love if you can ever provide an example yourself. And looking to the future, as I said, we're kind of moving forward. We are on track now to have 2 new releases scheduled per year. So we have 2.1 coming up in November. And kind of looking further down the line, what does SunPy 3.0 look like? And what we want for this is to kind of upgrade the backend of map to be based upon NDCube, which is a SunPy affiliated package. And this will allow us to kind of upgrade the image data to not just be in 2D, but you can also have n-dimensional coordinate data. So this is very interesting for if you're looking at, you can have an image cube, for example, in time or in frequency space, and we can have now this functionality within map. And we also want to improve data support for different kind of spectral axes. At the moment, SunPy doesn't have a spectral container. So looking to the future, we kind of want to have this functionality within SunPy. We want to have a standardized approach to metadata. At the moment, it's not fully standardized yet, but we're looking to get there. And we're in the process of, we're nearly fully finished developing a package template for affiliated packages. And what we want this to do is to really be an incubator for instrument teams that were interested, for example, in converting their instrument calibration pipeline to Python, for example, but don't know where to begin, where SunPy can kind of help incubate that through our affiliated package template. And we really want to hope the community involvement more. As I said, the development team can sometimes be small. We want more contributors, whether that be from code or from feedback from users. So we really need to get the conversation going. And I think this is really kicked off the last few years with kind of going to conferences and doing tutorials. And now with the 2 new papers, we have a citable thing that can be cited. And so that's kind of an overview of SunPy. And I'm happy to take any questions.
Thank you.
So if I want to do, say, feature tracking or Fourier transform of some time series of some feature on the sun, are these, is there a guide to what packages I can go to and how I can do that kind of stuff?
Sure. So I guess it would be kind of using the kind of tools that are available within the Python ecosystem. But what SunPy will allow you to do, for example, is to read in all the images into a data cube. And then you can have it as an array, for example, and then you can then use all the packages that are available, such as like SciPy or Skimage or anything like that.
Well, SciPy is not going to give me feature tracking of, there are various kinds of feature tracking algorithms.
Yeah, no, for sure. So I know we do have some development within SunKit Image, which is another affiliated package of SunPy. But I don't know if there is like a place you can. I mean, maybe just. I'm not sure of packages myself, but I'm sure there is feature tracking packages out there.
I'm just thinking going forward. I come into this and I have something I want to do, and SunPy gets me to step 1 at the moment, and I want to have a guide to what else is out there. Like there's a IDL astrophysics set of routines, all neatly separated out into types and all that, and you can download them and use them. That kind of thing, a guide to what's out there.
Yeah, I guess I'm not too sure. Is Jack on the line? Jack, do you know of any? I don't. Like SunPy doesn't host a guide like that. But
so, Aaron, for your specific question on feature tracking, then that is in SunPy. I know that because I wrote it, but it does. It does rely on something in. It relies on a function in scikit image at the base. So there are. That's part of the. Rather than rewrite a feature tracking algorithm again, or copy them or re-implement. Say that again. Sorry.
There are multiple algorithms as well.
Yes, I just picked one, and it works. Scikit Image does provide like a feature identification feature, so I just use that rather than me trying to write my own. So the more like solar specific stuff we're trying to keep in SunPy, like solar differential rotation now is very well supported in SunPy using the coordinate transformation framework. So yeah, we do. But if you want to do going from like manipulating the data in a solar physics sense to manipulating the data for like a scientific application, then the expectation is you drop down into using like SciPy or NumPy and things like that after doing your manipulations in SunPy.
Yeah, and just so we're like, if you're looking for something to be done in SunPy, we're trying to put that now into Sunkit Image. So that's where that feature tracking is now, Jack. And I've just linked it there. So if you want something, you can contribute to put that there, or you can ask, raise an issue to say that you would like to see it. It's something we'd like to develop further, but again, we need people to actually do it.
Thank you.
There's a question from Veronique. Veronique, do you want to ask your question yourself?
Yes, no problem. No, it was just about standardized approach to metadata. This is a bit big. What do you really mean by that, or what will it imply?
So I guess it's like so at the moment for our two different types of data containers, we have time series and map, and we have made our own kind of meta dictionary, but we would like to have kind of a standardized metadata container that maybe is standardized between the different data containers that we hold within SunPy. What we really mean, I think a lot more discussion needs to be had on that. But do you have any feedback, or what would your interest be? Have you done this yourself?
So this is a question for me. No, I mean, because we were talking yesterday about metadata, EPN about space, of course, EPN tap. And so I was wondering what was your need, first of all, for metadata, and yes, how you will use it. That's the question also that we have. It's very nice to have a model for metadata, but then how is it used? I guess in the case of SunPy, since you have so many data, it will be valuable to have a common way of describing them. But I guess with Fido, you must do that already somehow.
So I guess with Fido, it's just a search for the data and download the data. It's not about like loading in the data. And then with say loading in the data, our metadata object at the moment is really kind of standardized to the way the fits meta headers are, which is a problem when then you're not reading in fit style files, right? So I think that's maybe where the need comes from. So an example of this is we're trying to develop now an etcdf reader, and it doesn't conform to the way a standard fits header would be. But at the moment, our meta dictionary kind of container was built for a fit style header. So we kind of want to make a standardized way, but it's challenging for sure. So the idea would be that you read in a file and you have a meta dictionary, a meta dict structure, and then you have your data associated with it. And we want to have that standardized for our different data sources that we read in. And we've just been lucky so far that a lot of the data that we would read in are fit style. But moving forward, we don't want to be constrained by that.
Of course, there are lots of readers out there for various things.
Yeah, so it would be, for example, like using a reader, but then having it. So, for example, there's lots of netcdf readers that we will then use, but then when we read it in, we want to have it in. We want to take from that the metadata into a similar structure that would be from a fits file, for example.
And you probably need also a mapping between the two dictionaries, because the keywords or the values would not be exactly the same, and you want to be able to interpret them correctly.
Exactly. Yeah.
Well, I know at one time there was sort of an effort to develop a standard model for Python. What's the status of that? Has NDCube kind of become the standard?
Yeah, that was discussed at some point.
Well, I can step in here briefly too, because we're hoping to hear back, well, I guess we'll hear next week, to coordinate between SunPy with NDCube and SpacePy and Happy to work on at least translating common data models back and forth. So if that proposal doesn't go through this year, we'll keep pushing. But we think that's a good idea to be able to link the different data models. Coming up with the unified data model with a small HDEE grant was not really in the cards. I mean, but at least to map back and forth at the beginning, and then we promised to look at, well, what could be a common thing if we were looking at that for the future.
Yeah, somehow that slipped my mind, and yeah, that would be a great project if that gets funded.
With all the people at this meeting, lots of us are working on mappings between these things. We just need to agglomerate all that information and, try to use what we already know as a community to get it done.
I mean, it took over 10 years for SPACE, so it's not easy.
Say that again?
It took 10 years for SPACE to come up with a common, here's what we're going to use for everybody, all these different projects. So and a lot of these Python efforts are fairly mature, so ripping out their fundamental lowest level data model and saying, we're going to change that, that's hard.
Yeah.
It only took 4 years to get to SPACE 1.0.
So maybe this is a naive comment, but there is a description with unified content descriptors, which is not a data model, but which can be seen as a glue, as a buffer between different metadata model. So you can always describe your quantity with a set of unified content descriptor, and after that have different name for, with different metadata model. And okay, that can be a first step towards afterwards unifying and developing a general model. I don't know what Baptiste.
Yeah, I can. I think we would need a little bit deeper presentation of what UCDs are. Yes, it could be the glue, as you say. I don't think we have time to discuss this now, but this is a good topic for the working groups.
I'd like to offer one observation though. The data DOIs offer kind of a way to bridge some of this, because there's a core set of metadata, very simple, in the DOI, and a way to map to expanded metadata, and you give the type, whether it's SPACE or whether it's PDS or whatever it might be. There is then a core set of metadata that's common across all of them, and it could be a way to bridge. And also the community kind of expects it for data now for publication, so kind of fits into the culture in a way.
Well, one thing that is done also sometimes is to have extended MIME types attached to files. So you have the basic MIME type that tells it's a FITS file, and you can add an extension that says what is the standard for the metadata that has been built in. So that's also a kind of thing that you can do.
Yeah, right. But that only works when they're self-documented data, right?
Yeah.
The devil is details in many of these things, because it's nice to have a solar image, and it's got intensities and wavelengths and all that, whereas the space physics domain is going to have a distribution function with angles and energies of particles, and it gets very hairy very fast, as many of you know.
Oh, I'm sure the sun can be hairy too.
We've talked about this, Jeremy and I, for this interface concept, and this could apply to Happy as the sort of next layer above what Happy is, because Happy gives you access to the numbers with minimal metadata, but then what you need on top of that is a kind of science data interface guarantee that says, if I want mag data, it's going to look like this, and I can make this request and know that I'm getting mag data. And then, but that requires another layer of mapping to say, well, based on these column names and these structures that I found in this data set, what scientific quantity does that represent in some kind of standardized way? That's the next layer on top, even of ISTP.
This is exactly what Veronique is talking about. And so there is already a set of keywords that are really high-level description keywords of parameter type. So is it a magnetic field, an electric field? Is it a time, or is it a coordinate, or whatever? And so this can be described. There is a set, and we have been extending this set of descriptors. So this is part of the astronomy virtual observatory standards. And so in the last years, we have been extending that set of keywords to include planetary science and solar system and solar observations. So this could be done, and this is exactly the glue you are talking about here.
Yeah.
A generic keyword that tells, okay, I'm looking for magnetic field data. So you know exactly what is the keyword, and then you can search for this.
Right, but then to have a guaranteed interface that says, here's how you get that data, regardless of its storage format, that you're going to get an interface that looks like this, that just takes care of it for you, and you get function calls that give you back that stuff in the right units for whatever. That's
the job of Happy.
Yes.
Yeah, that's what I thought.
Yes, but Happy serves what's in the file right now. This would require potentially rearranging things. But if there were descriptions in what you just mentioned here, that could be largely automated.
Yeah.
Well, actually, couldn't that be resolved internally by Happy? A Happy server doesn't have to give you exactly what's in the file.
Yeah, but if you want to interpret B_00 as either the magnetic field magnitude or something else, you have to know that. It's not able to infer that necessarily, depending on what the field names are.
Yes.
Well, I kind of thought it would be a smarter Happy server, I guess. If you say you want it, say in standard mag format, which might be a BX, BY, BZ, B total, time, whatever, the smart Happy server would transform the underlying data into that format.
So this joins back to the discussion of that Chris started on VO table yesterday, because what we are talking about is in the header of the columns of the VO table. And this is why the UCD is there. It's just to tell, okay, there is this name for the column, but the quantity is magnetic field, amplitude, or whatever. Right. And this is why it serves. What is the use of this? Veronique has put the link on the UCD standard on the notes, not on the chat, but on the online notes.
I want to point out, that I'm sorry. Go ahead.
You were breaking up, Lee. Go ahead.
Yeah, we're getting off our schedule.
Yeah, we are a bit late.
I want to make sure that, Phase is capturing this information, exactly what you're talking about.
Yes, this is the measurement type, but it's a bit, we started to, well, it could be discussed, and this is probably the working group topic also. Right.
Yeah, it's not quite capturing it in space. It's close, but it's not enough.
It's close to that. Indeed, the measurement type of space is close to this and could be used for our community. It's difficult to extend, but yeah.
It is capturing things like component.x, it's capturing magnitude, it's capturing all these things that define a vector. So it is in there.
Yeah. Okay, so I propose to go to the next talk. So, Eric, the thing is that I don't know if you saw on the agenda, but you had 3 minutes.
Yeah, so
for
I have
2
15 slides, but I think I can get through them really quickly.
Okay, yeah, 3 minutes is short, so that's why I was proposing to have 2 slides. But okay, let's go.
I think I can technically fit everything on 2 slides, but I just have a lot of screenshots.
Okay, good, let's go.
So I'm Eric from SpeedUs team, and I've been working on PySpeedUs, and that's what we're going to talk about today. So getting started, we're doing all development on GitHub. So it's github.com/speedus/PySpeedUs, and that's what we're treating as the bleeding edge. And we're also doing all of our documentation on GitHub. And internally, PySpeedUs uses PyTplot to load the data into variables and create plots. And underneath that, it uses CDFlib, which is the same tool that HelioPy uses. And so I just have to say a lot of the work is actually being done by the Maven team and the PyTplot team at LASP. And yeah, they're also doing work on GitHub. And so getting started, we're using PyPI for our releases. So to install it, it's just pip install PySpeedUs or -- upgrade if you want to get the latest version. And another important thing is setting the data directories. By default, the data are placed in the directory where the PySpeedUs is installed, but you can configure this with environment variables. So if you set speedus data dir, it'll update your data. It'll change the directory where the data are actually stored. And most missions have their own environment variables, which can override speedus data dir. And it's important to note that these environment variables also work with our latest IDL versions. So if you load data with IDL, PySpeedUs should automatically find the exact same files locally. And so you can easily share data between IDL and Python just by setting the environment variable. And so we use different data sources for the different access to the data. And these depend on the mission. So, for example, for MMS, the default data source is the official science data center at LASP, but the data can be loaded from SPDF using just an SPDF option to the load routines. And most other missions, but not all, use SPDF by default. And we have over 20 different projects currently. And I include a list here. The list is also on GitHub. And it's important to note that while we can load the CDFs from most instruments from all these missions, the post-processing of the data products for most missions aren't at the same fidelity as our IDL tools. MMS is the furthest along. I think MMS is almost exactly the same data products, with the exception of our tools to analyze distribution functions. But for example, Maven, our Maven tools in IDL we have over 120,000 lines of code, and we obviously don't have that yet for Maven and Python. So the load routines are just simple functions that follow the general form PySpeedUs.mission.instrument. So for example, for MMS FPI data, it's PySpeedUs.mms.fpi, and for RBSP emphasis data, just PySpeedUs.rbsp.emphasis. And if you don't give it any options, it loads some default data. And so just like with our IDL routines, the options are set with some standard keywords. So like, for example, T-range sets the time range, level sets the level of the data, and plus there are many, many more. To see a full list of the keywords supported by a load routine, you just use the Python help function on that instrument. So for example, PySpeedUs or help on PySpeedUs.mms.fpi returns this screen, and this is cut off. There are many more keywords supported here. So this is just all the options supported for MMS FPI, or some of them. So a simple example, just loading some MMS FPI data, we just import PySpeedUs and then call PySpeedUs.mms.fpi and set the keywords that you want to set, and it loads it into PyTplot variables. And then you can import tplot from PyTplot and call tplot on those variables, and it creates a nice window. and internally PyTplot's combining the data with the metadata, the plot metadata, and so you get these nice plots. So we're doing testing using GitHub Actions to run unit tests that load the data. We currently have more than 80% test coverage, and these tests are run every time we commit to the master. And we're using IDL to validate that the data products actually match the same data products from our IDL tools. So we have unit tests in IDL that can load the data in IDL, load the data in Python, and check that the data products match. And we have this fancy tool now called SPD Run Py Validation, which runs a Python script and checks a list of variables to make sure that they actually match the data that are currently loaded in Python. And these examples are all just from MMS. And we have, I think, more than 20 now validation tests just for MMS data products. And we're using Jupyter Notebook to create examples. To find these, also just go to github.com/speedas. MMS has its own, we have a whole lot of them for MMS. So MMS has its own repository. And we also have multi-mission examples under PySpeedas examples. And that's all I have.
Thank you. Just one question, and when you have your cross-testing between IDL and Python, you are using the IDL Python bridge or something else?
No.
Okay.
Nope. This function actually creates a script and then runs it. The reason for that is because I run these on older versions of IDL as well, but the Python bridge doesn't work so well.
Okay. Thanks. So I propose to go on, and then we have the discussion. So next was Komodo by Darren. Darren, are you online?
Yes, I'm here and ready. I'm assuming you have the slides.
Yes, I have the slides. Yeah. But since we started in an awkward way, if you have them, maybe you can share them.
I can do that too.
Yeah. Sorry.
I can. All right. Is that showing the presentation version?
Yes.
Okay. Okay. So, quick Komodo overview. You can see the movie I made with the longer version, but Komodo is an official NASA open source project, and it's got a GitHub repository, documentation, and site for the web demo is listed there. The one thing, when we're trying to import new models into Komodo, we call this Komodification. So it's basically a way of saying, are you able to access your data from Python? Have you provided all the interpolating functions you need to do it? And have you followed the proper metadata and naming standards to develop this? Then a model has then been incorporated into Komodo, and a lot of the visualization and analysis tools become available to you. The development so far has been mostly through the CCMC, and we're really looking to broaden our involvement from the community and looking toward more contributors as well as we do this. A quick little sample of what Komodo can do, just a quick little highlight. These are actually images that were created through the web interface to Komodo. But you can see we can load in multidimensional data. The one on the top left is multiple slices through an MHD code. All of these images can be, rotated, zoomed, probed for values, things like that, and you can interact with the data and try and see it in a more dynamic way. But the data can be displayed in lots of ways. Particularly the one on the bottom left is actually combining two things. It's actually using commodified data through HAPI, grabbing the GRACE satellite data, grabbing the model data from GITM, and extracting along the satellite trajectory the values in the GITM model. And while we're doing that, also we can provide a little error box and did a plus or minus 100 kilometer error, and you can actually see then that lighter blue shading gives you the ranges of value. So this type of analysis can be quickly done. And again, probing and zooming in where you want to see this actual data here was also interpolating in time and was a week-long run. So I'm just showing a small snippet of it. But again, from the page before, go to the web demo, go to our documentation. There's lots of information there, and we'd love to have people contributing to the project. So thanks.
Thank you very much, Darren. For HelioPy, Arnaud, no, PlasmaPy, sorry, I will stop skipping people. Nick? So, do you want to share your screen?
Yes.
Or do you want me to do it?
Actually, if you could share
okay.
technical difficulties.
Okay. I hope it will not be difficulty for me either. To slide. Nope. Okay, let's do it this way. So, quick and dirty, it will work. Share. Yes. Can you see it?
Here it comes.
Yeah, the two slides. So
Okay.
let's do it. Okay, like that.
That works. All right. So I'm going to talk briefly about PlasmaPy. Plasma physics and heliophysics are very closely related. So if we're developing a data and software environment for heliophysics, then we also need plasma physics functionality, including connections to laboratory experiments on heliophysical properties. So we are developing PlasmaPy, which is an open source Python package for plasma research and education, and is currently under active development. And our long-term goal is similar to PyHC, but for plasma science, to develop a software ecosystem. So next slide. There are a couple of possibilities for IHDEA and PlasmaPy collaborations. So for laboratory plasma science, there are few things that are comparable to, say, SPACE, and that makes it harder to develop shared analysis tools. So one thing that people in laboratory plasma science can do is emulate what we're talking about in this meeting. And also, we want to be able to foster interoperability. So because a lot of heliophysics processes are studied in the laboratory, we want to make it so that we can use the same tools and standards to study both laboratory and space plasmas. And that can be beneficial for both fields. So that's it.
Thank you. Shall we? Yes, let's go to the next one. So, yeah, I'm not skipping anyone here. Arnaud. Yes.
Okay. So yeah, well, this short presentation is not the general presentation on HelioPy. It's just focusing on the access to solar orbiter data. So here you've got a list of examples that are provided, and I wanted to point two things before the access to solar orbiter data. Is this SPICE orbit plotting that you can do within HelioPy,
yeah.
And also that the latest version has all SPICE kernels now automatically furnished when they are loaded, so they are up to date. For the now, and there is also one very interesting thing with HelioPy is that not only it downloads the data that you request to visualize them, but it also allows to save them on top of the original format in HDF files for quicker access. So if you request again part of the same time period, it will it's loading very fast. Now moving on to the second slide. Yes. So this is some quick code I took from their examples to display solar orbiter data, so magnetic field. For the moment, it's only magnetic field, but it does what it says. You know, it really downloads and computes the module and plot the radial component and download all the files from the SOA archive at ESA. And yeah, this is I think it's very useful, and they implemented that very quickly the day or the day after the release of the data. So that was quite impressive. So yeah, you can visualize solar orbital data through HDEA. That's the take-home message, and that's it.
Thank you, Arnaud. Okay, so we are done with the presentation for today. Any questions on the last 3 talks or 4 talks?
I have a question for Nick Murphy. The comment that you said that there's not a good translation between, say, space metadata and experimental plasma physics. That's a curious statement, and I'd be interested in talking to you more about what the discrepancies are and how we can make them, consistent. So that could be a discussion for tomorrow as well.
Yeah.
Because in heliophysics, we do have active experiments. And of course, it's not the same as laboratory experiments. So I think there could be some analogy that could be drawn.
I think we have about 3 days of topics for our discussion tomorrow.
Yeah.
That's all?
Yeah.
I was thinking more.
I had a question for Darren about the Komodo stuff. Is that because I wondered if there's a way to do a happy analog for model requests where there's some interface that can sit on top of any kind of model. Is that what's the framework structure that you're using to separate out? Okay, there's this model underneath, and then here's how you make requests. What is is it a Python specific API, or is it an API that you could expose as a service?
Right now, everything's running from within just the Komodo application, but we are in development for kind of a Komodo server, which would basically have its own API to request data back.
I would love it if that was
multi-dimensional data.
Mm-hmm. Yeah. Is that, I would love to be a part of that API development piece, just because there's multiple, if you get that right, multiple institutions would use it.
Right. And we're right now working through kind of making sure our proof of concept works before really trying to go super broad with it. You try and solve everybody's problems and it takes forever to solve, right? So
yes, right.
At some point, yes, in the near future, I will definitely bring you in on what we're doing and see how we can make it usable for other groups.
Yeah, there's plenty of folks at APL who do model development and are thinking similar lines about, okay, server with model and then remote client that does display of just images that get sent, right? I mean, Amazon just launched an entire 3D gaming thing where all the calculations are on the server and they stream you just the game video. So maybe it doesn't work very well. But the timing is not quite as critical for model analysis. If we had a similar approach where the server was doing the heavy lifting and just showing you what's on the screen, you could maybe do something like that.
Yeah, I think I'd like to be involved in that too. That it sort of reminds me of, the DOS2 server. You can call back to the DOS2 server and have it use Spice kernels to calculate parameters, right? So it's just a model essentially. So you essentially say, for these times, send me back the data. So it's very similar to Happy, but tweaks to the interface would be needed.
And we're one of our initial focuses is on just subsampling the data. It's like contact and say, hey, give me just the values on this slice. Right? So you're not sending big chunks of data back.
And you've got the important step where the model is responsible for its own interpolation. I think that's critical.
Yeah, we made that choice early, and we're happy with that choice. But it's a little more complication, but it's going to be a lot more powerful that way.
Yeah, that's your story, and you're sticking to it, huh?
That's right.
Yeah, no, that seems good, because modelers will get very nervous if someone else is doing the interpolation. No, I like it. Thanks. Yeah, that's good.
So, John, just to you, you might talk to Larry Brown about Q functions. So, we have Q data set to model the data, and then we had Q functions as well, which is an object that you can use to query models and things like that. So it's analogous to that.
Very good.
So, well, if there is no other question, I propose to adjourn for today. I have a meeting in 5 minutes, so that falls very well. Okay, so see you tomorrow. We'll try to. So I'll send an email to the co-organizer to see how if we can try to summarize by tomorrow the ideas that were proposed for working groups, so that we can start the discussion. Okay. So Xing and Arne start the discussion. Okay.
Okay.
So Xing and Arno, I will send you an email.
All right.
Okay.
Sounds good.
Okay, so have a good night and a good day if it's not the night yet. And bye-bye, see you tomorrow.
Bye.
Bye.
Thank you. Bye bye.